Here, we observe a heavy, solid copper wire resting entirely inert on a dark, textured laboratory table. But if we switch on the electrical current, the metal lifts off the surface and hovers steadily in midair. We know that magnetic fields exert physical force on moving electrical charges, but this wire is a massive stationary block of solid metal. It appears to have no moving parts for an invisible field to grab. This lift doesn't originate from the wire as a single macroscopic object. Instead, the force begins at a scale far below the surface of the metal. To understand this, we look to the Lorentz force. When a single electrical charge moves through a magnetic field, it experiences a physical push. This force occurs at a perfect right angle, perpendicular to both the particle's travel direction and the magnetic field. To explain our floating copper wire, we must apply this single particle rule to a massive river of electricity. Zooming in to the atomic lattice of the wire reveals a rigid grid of stationary copper atoms and billions of mobile, free electrons. When the current flows, these electrons stop bouncing randomly and move together with a unified drift velocity. Drift velocity is the average speed that charged particles steadily attain in a material when pushed by an electric field. As an external magnetic field cuts through this lattice, we can see the Lorentz force acting on each individual drifting electron, nudging it sideways. That tiny, microscopic sideways nudge on one single electron is the source of the force required to lift the solid copper. Determining the total physical push on the wire requires counting every moving electron packed within a specific segment of the metal. We define the physical volume of this section by its circular cross-section of area, A, multiplied by its length, L. To find the population of electrons, we use number density, N. Multiplying this density by length and area gives the total head count of moving charges. The macroscopic lifting force is the microscopic Lorentz force multiplied by this massive internal population of electrons. The unsimplified equation shows force equals the number of carriers, charge Q, and the cross product of drift velocity and magnetic field. Grouping number density, charge, and drift velocity defines current density. Multiplying by area yields a single macroscopic measurement, electrical current, I. Current is a scalar describing flow magnitude, but cannot dictate which direction the force pushes the wire. We resolve this by transferring the vector property from microscopic drift velocity to the wire's physical length. Length L becomes a vector following the current. This transfer links the motion of the electrons to the solid object. The orientation of the wire itself now determines the direction of the force. This leaves us with a simplified formula. The total force equals the current times the cross product of the length vector and the magnetic field. We can now use this equation to determine exactly how much force is needed to keep the wire suspended. Let's apply this exact magnetic equation directly to the physical 200-gram copper wire we saw hovering steadily above the laboratory table. We have a mass of 200 grams, a length of 1.5 meters, and a steady current of 2 amps. To remain in midair, the downward pull of gravity, mass times gravity, must be perfectly matched by the upward push of our magnetic force. Calculation shows that a magnetic field of exactly 0.65 teslas generates enough upward force to perfectly cancel the weight of the copper. The transfer of force is purely mechanical. As the magnetic field shoves the drifting electrons, those billions of charges physically crash into the rigid atomic lattice of the copper wire. The cumulative momentum of these billions of microscopic collisions provides the physical thrust that holds the solid metallic structure firmly aloft. This interaction is the foundation behind modern electric motors, powerful industrial solenoids, and heavy machinery. Directing current through a magnetic field converts electrical energy into the precise mechanical torque required to rotate industrial turbines and propel electric transport.